Good morning. Thank you for joining us for A Day in the Life of a Netflix Engineer, Episode 3. My name is Dave Hahn. I'm a senior engineer at Netflix, and I will be your tour guide through this romp of the architecture of Netflix that makes all this fun stuff work. What we want to do is give you an opportunity to walk in the shoes of a Netflix engineer. And for us, this was important enough that we actually had shoes made. So we have a white set of shoes, and if will come out, for those of you that are a little bit more stylistically concerned than I am, we also have a darker evening pair of shoes available. So now taking a walk in the shoes of a Netflix engineer is both a little bit more literal and a little bit more meta. Let's talk about Netflix by the numbers. Netflix runs hundreds of billions of events through our data pipeline systems every day. These events are things like users navigating our UI, making decisions, pressing play on a piece of content that they'd like to see. It also includes those interactions that happen while that playback is happening. We get error logs and diagnostic information and performance information, and we get it not only from the devices in your hands and in your homes, but also from our CDN network that's actually streaming the video bits to you, as well as everything that we have running in Amazon. So we run hundreds of billions of those events through this data processing pipeline every day. There are tens of billions of requests handled by our edge systems every day to create your Netflix experience. We have billions of metric time series that we update and collate and aggregate and store every minute of every day. So between that data pipeline system and all those events and metrics, we're definitely not lacking for information. We stream hundreds of millions of hours of entertainment to our customers every day. At our peak day in 2017 so far, we streamed a little over 250 million hours of entertainment globally in a single day. There are tens of millions of devices that talk into our service every day. There are millions of requests per second through the front door to the Netflix service. We use hundreds of thousands of EC2 instances to answer those requests. And using autoscaling, we scale in and out tens of thousands of those hundreds of thousands of EC2 instances every day. We make thousands of production changes every day. And by that, I don't just mean, a little change to a database or inserting a new record. These are code pushes and feature flags and lighting up new code pathways. Last I checked, the daily average is about 4,000, which means that there's one change to our production environment every day for every Netflix employee. We run hundreds of microservices to create that experience. That's everything from our customer-facing software to all the tools and data and algorithmic systems that we use. We run tens of terabits of video across the internet every second. All of this is aimed toward a single goal. Now, for Netflix, what might that goal be? Might that be the largest content catalog available? Maybe. Could it be the fastest streaming available? Sure, that sounds good. How about a global reach? That one's good. We should probably have financial performance in there somewhere. But while they're goals, they're not that singular goal, that single guiding light that helps us make all of our decisions, that informs everything we do. So for Netflix, our single goal is more Adam Sandler movies. Well, maybe that's a goal, but maybe it's not that singular goal, although maybe it's an important one. So for Netflix, our single goal, our guiding light out there that informs our decisions, is winning moments of truth. Now what that means, when someone has time to spend time on entertainment, they have a decision to make. Watch TV or a movie or play a game or read a book. I hear there are some people that go out into the sunlight on occasion. But whenever they choose Netflix, we win that moment of truth. That's our single guidepost. Every decision we make is guided by winning moments of truth. It impacts decisions around the content that we purchase and that we make. It informs architectural decisions. It informs cultural decisions. It informs hiring decisions. It informs software decisions. Everything aims towards this winning moments of truth. For our customers, that looks like the ability to watch what they want, when they want, on whatever device they want. And so important was this to us that we recently added downloads. So now we can win those moments of truth when our customers are not even online. Our customers have a variety of devices in their homes and in their hands, and that variety of devices varies around the world. We've discovered that the way people interact with their entertainment is affected by and informed by the particular device that they use. So part of winning those moments of truth for us is making sure that we've customized those experiences appropriately for the particular device that you're using. Now, those mix of devices vary around the world, so we have to make extra effort to make sure that that's easy. Now, ease of use also has different factors. Language and culture are an important part of entertainment. So localizing our service not only makes it available to more people, but it allows those people to draw closer to their entertainment, to their stories. Moreover, as we move throughout the world, we use language and culture specialists to ensure that those subtle meanings that the content producers intended, that those special turns of phrase are maintained and carry through that localization process as well, so that our customers' interaction with their chosen entertainment is simple and delightful and easy. Because we want to win those moments of truth with our customers. And that's a lot more than just pushing those video bits across the internet. It's producing and engaging and entertaining content that's meaningful and easy to access. So now that you understand a bit about what informs our decisions and how we make those decisions, let's talk about the architecture that's required to win those moments of truth. When you're using Netflix, your experience is made up primarily of two pieces. We run quite a few things at this cloud thing at Amazon you may have heard of. And all of our video bits are produced by OpenConnect, our purpose-built video CDN. We started building OpenConnect a few years ago. Before then, we streamed video content from those big-name CDN providers that you've heard of. But as we looked forward, we saw some challenges coming at us, that as more things became high definition, and we moved to HDR and 4K and 8K and all of the other Ks that are coming, that if we wanted to maintain a high-quality experience for our customers, we were going to have to get those video bits as close as possible to our customers' streaming devices. So the initial answer was simple. We will put a caching device in every customer's home. Surprisingly, that was a little impractical. So we had to do the next best thing. We built caching devices and we installed them at internet exchanges and right inside of ISPs all around the world. Now that we've been at that for a few years, OpenConnect devices exist in thousands of places around the internet. As many places as possible, we put them right inside your ISP's network, so that when those video bits are coming to you, they're on the shortest path possible. You don't even have to transit outside of your ISP's network. And that makes sure that as you're watching things in 4K HDR, that your experience isn't interrupted or degraded because those video bits are as close to you as possible. This is a map of what the network looked like a few months ago. Since then, hundreds, if not thousands, of new devices have been added. Those orange dots represent internet exchanges or peering points where we've installed a large cache set so that people can connect into us. All of those green dots represent caching systems embedded inside of ISP's networks, so those bits are as close as possible. OpenConnect itself is a highly optimized system. Depending on the popularity of a file in a certain place, it may be served out to people from memory, or from solid-state disk, or from spinning disk. We also split that content across multiple machines. We have a bit of a video streaming-like load balancing algorithm that ensures that we've connected people appropriately to the caches for a continuous video stream. We found that it services our customers better than traditional things like connection-based load balancing. For other interesting optimizations, we have some boxes that have 100 gig network adapters in them. And our goal is to make sure that as much of that 100 gig as possible is the video bits going out to our customers. That requires a good amount of optimization. At this point, we're able to stream a little over 90 gigabits of TLS video data out of a single 100 gigabit network adapter, and we're getting closer to adding a few more on top of that. So for more of that long tail content, the stuff that not quite as many people enjoy, we have boxes built out with hundreds of terabytes of spinning disk so that that information is available as well. And the people watching the less popular content still enjoy just as high quality of an experience. We're also commoditizing. Those of you that have looked into OpenConnect in the past realize that we just build this with hardware that you can buy as well, and we share what those designs are. Lately, we've gone even a little bit farther to move towards commodity switching and routing. We recently pulled all the Cisco ASR and Juniper and MX devices out of our networks. So highly optimized on commodity software and hardware. If you're more interested in some of the details, you can go to openconnect.netflix.com. The teams behind it also publish quite a bit on our tech blog. So OpenConnect services all of the video bits that you see coming from Netflix. Everything else is on Amazon. All of that business logic and customer data and caching layers and persistent systems and algorithms and tools and things that build out UIs all run on top of Amazon. Currently, Netflix runs out of 3 Amazon regions. We are in US West 2, US East 1, and EU West 1. And we make sure that we always run in 3 zones in any of the regions that we're live in. When we first started with Amazon, we were in a single region in US East 1. As we started adding more international customers, we realized that perhaps having to transit an ocean all the time to talk to us wasn't the best customer experience. So we launched our services in EU West 1, and we started creating an island model. Our EU customers would be served in EU, and our Canadian, US, and Latin American customers would be served in US East 1. So we reduced the transit time for some people, and we reduced the blast radius of certain failures. If something happened in the EU, it would unfortunately affect my EU customers, but only them. But that highlighted another problem. Now, while the blast radius is reduced, we're still affecting customers. So I thought maybe there's more we could do. So we launched in US West 2, and we also changed the way we thought about things. We decided to go to a global services model. And the big goal with our global services model was that we should be able to serve any customer from anywhere in the world from any Amazon region. So that meant we had to have all of our data in all 3 regions. All of our caching systems had to be in all 3 regions and hot with the latest data. All of the applications required to service our customers would have to be up and running and healthy all the time in all 3 regions. If we dig into what those regions look like a little bit further, our customer devices connect in through our front door. Currently, classic load balancers are that front door. So of those devices, there are 2,200 or so individual device models that Netflix supports. I also find it interesting we've never retired support for any device that's ever streamed Netflix. So that Blu-ray player from 2009, still streaming. So those 2,200 devices connect in through the classic load balancers. Those load balancers are the front door for our service. Currently, globally, we run about 2,400 load balancers. The load balancers connect into an application we wrote called Zool. Zool's our layer 7 proxy router, business intelligence kind of, we need to figure out where to make packets go. So devices come in, they go to the ELB, they go to Zool. Zool takes a look at that data, our current rule sets, things going on in the environment, and it makes a decision as to where to route that particular request into the series of microservices that live behind Zool. I mentioned earlier we have hundreds of those microservices. This is an overall block view of how those are organized. Zool talks into our edge services. Previously, our edge service was a bit more of a monolithic service. Over the years, we've broken that up into a more traditional microservices architecture. Those edge services talk to mid-tier services. Mid-tier services talk to persistence and caching services. We also have batch and tooling services that talk to persistence and caching services and mid-tier services. So I suppose as much as we can call it a traditional microservices architecture is how Netflix is put together. Now, for the longest time, we ran all of this on EC2 instances. But there may be a few of you in the audience have noticed that there's a little robot on the screen now with a very happy can-do smile. We call him Titus. We wanted to take advantage of what containers could do. We wanted that more fine-grained control over resources. We wanted all the advantages that local development gets from containers. So we started looking around for a container solution. But we had a couple of goals that were very important to us. The first goal was that whatever we selected would have to be as easy or easier to deploy on than our EC2 instances. And secondly, that whatever that solution was going to have to tie into the Netflix platform that already existed in such a way that it wasn't harder for our software developers to use the new container platform. So it had to be easy and it had to tie into things. So we looked around at a lot of options that already existed for container orchestration and management. We found some of them were more oriented to you running your containers on your own hardware in your own data center. Other ones that were a little bit more cloud native required we think differently about our networking and our configuration and our service discovery. So they didn't meet our goals. So we decided to use some things that existed, things like Apache Mesos and Docker, and we would build the other bits that we needed to satisfy those other two goals of ease of use, and tying into our platform. The result of that is Titus. Titus now runs quite a few things for Netflix. But there was one other thing that we needed. As we start talking about containers, we started in doing batch loads. You need scheduling capability. The schedulers that we found didn't meet a couple of our goals. Many of them required a kind of one-size-fits-all approach to scheduling. Other ones didn't give us the capability to tie into the rest of our network and information and resources in order to make those decisions. So we built Fenzo. Fenzo is a pluggable scheduling system that allows us to provide great detail about what a particular job or system is going to need to do. And it understands not only the resources required for that job, but the current resources available in our systems, and helps Titus appropriately launch, schedule, and complete those jobs. So there we go. There is your architectural brief overview. Now, there are lots of interesting things that I could talk about for Netflix, and if I kept going, most of us would probably be here till about Thursday afternoon. Surprisingly, there's another talk scheduled in here after this, so I'm going to have to limit a little bit what it is we get to talk about today. For those of you who've seen earlier versions of the talk, I'm going to avoid covering some of that information and instead go into some new things and other bits that I find interesting about how Netflix approaches solving this problem. One of those things is networking outside of the cloud. When we start thinking about things that affect our customer experience, one of the things that becomes very evident is that there is a whole lot of network between my Amazon and OpenConnect resources and those devices you have running at home. One approach to this problem is, well, that's the internet. It's not really my responsibility. Those of you who've heard Netflix is responsible for the internet, that's not true. We use quite a bit of it, but we don't have that much control over it. But we wanted to look into, are there things that we could do to make our customers' experience across this network we don't control better? So we started looking at, a map of the internet. We realized there's a lot of pieces out there. There's a lot of different networks connected in different places, lots of large networks and medium-sized networks and small networks. So, well, that's easy. What we'll do is we'll just build a device and we'll just send it out to the internet. So we built a device, proved to ourselves that was the easy part of the problem. What we really had here was a logistics problem. If we look at this small map of the internet, trying to get my probes to all of those places is difficult to begin with. And the internet, surprisingly, is a changing thing, so I'd have to keep up with that as well. So when we approached that problem, like, well, maybe we can dial it back a little bit. Maybe we don't have to have probes everywhere, right? We'll avoid some of the smaller areas. That didn't change the picture by much. Well, maybe we'll dial it back a little bit further and we'll extrapolate, because extrapolation is a fabulous way to get accurate data. We thought, well, maybe we can this, or maybe we can that, or maybe we can this other thing, and we decided, well, maybe not. What we wanted was the information on how the internet was affecting our customer experience. We also wanted to make sure we weren't suffering from the tyranny of averages. So it's horrible to assume that everybody has an average experience. While some will be better, there's a good number that will be worse. And we wanted to have that data to use. So we thought about the problem again and realized, we have a lot of devices out on the internet and different networks that are talking to our systems every day. What we needed to do was look a little differently at the data we already had, perhaps enhance it or change it a little bit, and then we'd be able to get those models. We'd know what connectivity to Netflix was like for anybody across the world on any kind of network connection. So we got that data, we collated that data, we ran models across that data, and we created a heat map. Now, as I'm sure many of you know, a heat map is an excellent tool for solving practical problems. Right, I'm able to take my heat map, I'm able to put it in front of my software developers and go, you see all this bad stuff, you should come up with a better idea. That worked about as well as you would expect. So what we needed to do is we needed to really place this problem in the laps of our engineers. So, engineers are great. You give them a problem, they go solve the problem. So what I needed to do was take my engineers and put them in a place where they could experience all of these network experiences, even the bad ones. The darker things got, the worse it was. Answer was simple. What we'll do is we'll just invent teleportation. Once we have taken care of practical teleportation, we can just send our engineers all around the world and they can plug devices into these networks and try different solutions and coding up some different things and we'll fix everything. Again, a little bit of research proved to us two things. One, we don't know how to invent teleportation, and if we did, it would probably be outside of our budget. So we did the next best thing and invented virtual teleportation. We put together a device we call the Magic Modem. And what the Magic Modem does is it uses all of that data that we collect from real customer experiences and simulates them for all of our software engineers. So now instead of having to look at a heat map and decide that connection timeouts have this kind of wave and pattern and degradation and try to come up with something that fixes that, they could code something up and try it out and see if it even got better. So we at least invented virtual teleportation. This is a view of Magic Modem to kind of prove that it is actually a thing. So over on the right-hand side of the screen, you see the Magic Modem, and on the left-hand side of the screen, you see a terminal from a device connected behind the Magic Modem. As we select ISP profiles 1 through 4, you'll see that traffic pattern actually changes. So now if I access the service or hook up a device, I can experience the network from all around the world. And it's rather important. Because it's one thing to say, well, I know this UI change is going to make this better. It's something else to actually realize that the additional 40 requests that making that UI better requires is really a terrible experience for a lot of people. So we simulate the time, we simulate any packet loss we found. It's really a great tool. Now, those of you that are paying a little bit closer attention will also notice there that packet in sequence 42 arrived before it was sent. We discovered this was true across the internet as well. So while we were not able to invent teleportation, we did discover time travel. Or that there are lots of bad clocks on the internet, I'm not sure which. But now by understanding that information, by marshaling what we understand of that network outside the cloud, I get the result of a better experience for my customers that exist on networks that aren't the 100 gig network that we have at the office. And I can create a better customer experience and win more of those moments of truth. So we talked a bit about networking outside the cloud. What about networking inside the cloud? Now, many of you may say, but Dave, Amazon runs the network inside the cloud so that I don't have to. Well, it's true. I can't argue with that. But is it possible that having a better understanding of how your applications behave on a network that you don't run, you can't see, you can't configure, and you can't tweak might improve the experience for your users and give your designers some more information to work with? We thought so. So Netflix has a cloud network engineering team. They'll actually be presenting in this room tomorrow to go a little bit deeper on some of the things they do. So we have a team of network experts that design tools and help our software engineers make better decisions about running their application across a network. One of those examples that I like is a piece of software called Dredge. What Dredge does is it goes through VPC flow logs, VPC flow logs give you information about every connection between every network interface in your VPC. We also use some CloudWatch logs, and we enrich that data from our deployment system called Spinnaker. And what it gives us, what it fills in, is a gap in network understanding. So here's an example. We have a piece of software called Themis. The people responsible for Themis, when approached about what dependencies do you have, they said, we have one. We talked to a Cassandra cluster. So when we look at changing our software, all of our tests are around that Cassandra cluster. When we do chaos testing, it's around what if we can't talk to the Cassandra cluster. Well, we bring up the dredge information, and there are 10 other things that they talk to. That's kind of staggering. If you're responsible for a piece of software, understanding what it talks to and how it works is kind of an important part of that job. Now, I think these teams are in the same place many of us are. I'm building a piece of software. I use some Legos that already exist. I go pull in a library here and a snippet of code here and something else here, and I assemble them together into something that does what I want. But maybe I don't necessarily understand what all of those pieces are pulling in or talking to themselves. Okay, great. So they talk to 10 other things. Probably not very much, right? It's really still Cassandra we need to worry about. Dredge also gives them this view. Not only are you talking to these other services, you're talking to them a good amount. So while the blue line there represents that Cassandra traffic, there's a very close number 2 and number 3 for talking to Kafka and S3. That's a good amount of what this piece of software is doing. So if they want to create a graceful degradation scenario or understand where errors are coming from, there's 2 other very large systems there that they need to understand on top of the other 8 that they're talking to. This is just a relative view of that traffic. Dredge itself I find to be an interesting piece of software put together by that cloud network engineering team. So it looks at VPC flow logs across all of our different VPCs and a lot of our different accounts. Currently, Dredge collects, analyzes, and enriches 7 million VPC flows every second. So what's the result of that effort and that investment? We have a deeper understanding of what our application is actually doing. We understand where those sharp edges might be. We understand how to actually create realistic failure and degradation scenarios. We also know how to test them. So traffic from outside the network and traffic inside the network is only part of the picture. We have to provide some guidance to that traffic. We have to drive those devices from different parts of the world into our systems. So we have a team that's responsible for understanding what it takes to get that traffic from devices into the Netflix systems. So that means they have to have a good understanding of the internet, how we're operating on top of Amazon, how our ELBs are behaving, how our scaling is working. And it's not a simple picture. So this is a diagram of the traffic going to those 3 Amazon regions. So here you're seeing 100% of network traffic for Netflix going to Amazon, to those 3 different regions. And you'll see the patterns are different. Those daily or diurnal patterns that move are different depending on the region. The peaks and valleys are different. So if I'm going to talk about managing traffic, I have to understand what my current traffic is in relationship to other places in this very minute. I can't just have a general model if I want to successfully manage global network traffic. So here's a different way of looking at that. Of those 3 regions, we do capacity planning in 2 different ways. So the gray capacity there is there for our daily diurnal scaling, for those normal patterns. And then the blue represents capacity we have planned for redirected traffic. Now, we redirect traffic for a few different reasons. One of them is very simple. If we see traffic end up in EU West 1 that we believe belongs in US East, we just redirect it from those Zool layers in one region to another. But we need to make sure that we have a little bit of capacity there available to do that. A little bit more important picture. What do we do if something happens in US East 1? Whatever that might be. There's a problem there. We're not winning those moments of truth and my customers are impacted. If I don't move the traffic, if I leave it there, what I'm doing is I'm inviting my customers along on this roller coaster ride of, boy, I really hope we figure out what's going on and get it fixed in time. Just hold on, you'll be streaming again in a moment. Again, not a great customer experience. So what we chose to do is make sure that that blue capacity is planned in such a way that now I can take all of this yellow traffic out of US East and send it off to the other regions. Sounds pretty easy to begin with, right? We just proxy and maybe update some DNS records, and all of a sudden US East 1 doesn't exist any longer as far as our customers are concerned. But there's a problem there as well. Now I've created a thundering herd of those millions of front door requests per second. There's a good chance now I've made things worse. I have these 2 regions I'm redirecting traffic to, and now I'm trying to actively knock them down as well. Not really a great plan. So our traffic team invented goat riding a motorcycle over a chasm. Surprisingly long name, so they went with Nimble instead. So what Project Nimble does for us primarily is manage what we call dark capacity. So we take a look at those applications that are absolutely required in order to provide Netflix the streaming service. And as those move and change, we have a set of instances that are already running, that already have the software loaded, that already have it warmed and ready to go. They're just hidden from everything else. And as soon as we need to do that redirection, that dark capacity is brought into the light, it's immediately available, it's up and running, and now I don't have a thundering herd problem. I have a thundering herd of happy customers that don't have to wait while I figure out what's wrong in US East 1. One of the questions that goes along with this is, well, why not just run all those clusters cooler? Why not just have that capacity running and taking requests all of the time? Fabulous question, I'm glad you asked. Part of the challenge there is that there's an amount of profiling that has to happen with these applications all the time. And if we're purposely running them cooler, we can't get that profiling information. Also, if I need to move capacity around and make some changes, that dark capacity is easier to move and change and mold because it's not taking any customer traffic. So what's the result of investing in something like Nimble and dark capacity? Maybe you've heard of Chaos Kong. That's that big lever that we can pull. We can get all of our customers out of any Amazon region. Because of things like Project Nimble and an accompanying project called Flow that manages traffic, if we sniff that there's a problem in one of our regions, we can completely evacuate all of our customer traffic in 6 minutes. So the result of that is winning more of those moments of truth when things don't necessarily go as planned. So talking about chaos, chaos is still very important to Netflix. It's an important discipline. We have a team that specializes in nothing but chaos engineering. We still believe chaos engineering to be that effort of testing and experimenting in your production environment to make sure that your distributed system is able to handle the reality of the turbulence of your production environment. So for Netflix, that started with Chaos Monkey. We decided that we do not believe that the loss of a single instance should affect your running application. So that's one thing to just say, to have a statement, to write up on the wall. But at Netflix, we don't have anything like a CTO or a grand architect or an architectural committee or these kinds of things that would maybe enforce this. So it's part of the brilliance I find in Chaos Monkey is that by creating it and running it, we've put the problem of instance loss right in the laps of our engineers again. We've made it normal and regular, and they solved for the problem. Now, anytime we get one of those emails that says, oh, by the way, we have to get rid of 20 instances because the hardware's gone bad or whatever it might be, we don't have to do anything special. So Chaos Monkey was a great start. We started adding other things. We had Latency Monkey and Security Monkey, and we built an entire simian army. And it did a lot of great stuff for us, but we found a few problems. It was rather difficult for our engineers to use because now they had all these different tools that behaved in different ways and had different UIs and different reporting, and some of them were kind of self-service and some of them kind of weren't. So we decided we needed to fix that. So we built a tool called FIT, which is a failure injection framework, which made it much easier for you to create all kinds of problems for your particular service and to make sure that it behaved as you expected. It was a great step forward, but it still lacked a few things. So now we've come up with CHAP. CHAP is our chaos automation platform. And it does all of those earlier things really well and a few extra things for us. CHAP is very self-service. You don't need someone to set this up for you. There's also another half that's very important to chaos engineering, is that you need to be able to get the results of those tests. You need to be able to understand what happened. Well, you can dig through logs and hope that kind of builds a picture, but wouldn't it be better if you had a system that understood what was happening and could tell you exactly what happened? Well, you notice on our CHAP logo there, he has a monocle. So we have a piece of software called Monocle. And what Monocle does is it watches these chaos experiments and helps to explain to you what it's found and what's happening. It also integrates a lot more safety than we've previously had in our chaos experiments. Early on, we'd instantiate an experiment for an entire application, and sometimes we learned that that application really had problems. So while we learned something, we brought our customers along with us. CHAP makes it much easier. It manages instantiating new resources on top of which it will actually run this test. So you get a target group, and you get a control group, and little bits of traffic are sent to them, and they match each other exactly, so you can see the results of this chaos engineering test without having to extrapolate or guess as to what the problem might be. Fabulous move forward for our ability to test things, reduce blast radius, and make chaos engineering easier for everybody at Netflix. So what are the results of investing in chaos engineering? Simply, the results are all those outages that never happened. We had the opportunity to find problems before they became too big, or before they hit the production environment, or before they impacted us winning those moments of truth. Another system I find to be interesting is media encoding. Netflix gets a lot of things from production houses and studios. We get this original media. We have to go through a lot of stuff and turn it into things that then you can watch. So before anybody asks the question, I'll let you know this is not how media encoding works. There's nobody running around dropping DVDs and Blu-ray players. As a corollary answer, this is also not how streaming works. So how does this actually work? We get source media from those production houses, and we spend a lot of time validating that media. We look for digital artifacts or color changes or missing frames that may have come from data transmission problems or earlier transcoding efforts. Any of you that grew up with cassette tapes and VCRs are probably familiar with that generational copying problem. By the time you got to the 8th one, you had no idea what was on there. So starting with that original source media being as perfect as it can be is very important. So our first step is to validate that. If there's any problem with it at all, it gets rejected. So then what happens is we go from the source media into the media pipeline. That spits out files, and now we're supporting your healthy lifestyle. So you can watch Netflix while you work out, or your more likely lifestyle. So we get the source media. We introspect it. We decide, this is fabulous. Now we have the media pipeline. A lot of things happen in that media pipeline. 2 words describe a lot of work. So here's a big block view of that particular work. We start out with that video source. And then we take that video source file and we break it up into small chunks. We do that for a few reasons. First of all, that source file is terabytes and terabytes and terabytes and terabytes of data. Oftentimes it's larger than you'd want to try to shim onto one particular instance anyway. It also allows us to parallelize that encoding work. To give you an idea of the scale of that encoding work, there are lots of different codecs required by myriads of those 2,200 different devices that we support. So each one of those has to go through its own video encoding process. The audio is encoded separately, lots of different audio codecs. So all of that has to be broken up and encoded with all of these different targets. Once each one of those chunks are encoded, we then go through and validate that chunk. Same thing like we did on the original stuff coming in the front door. We're looking for any artifacts or missed frames or color that changed in an odd fashion to make sure that we haven't introduced anything that's going to be kind of a speed bump in people enjoying their chosen media. And then we assemble that all back together. We stitch all of those chunks back together in all of these resulting files. And then we go through and we validate it again. This is what all of the bits of those processes really look like. There are over 70 individual distinct pieces of software that it takes to have that stuff work. It's important because we don't do any kind of dynamic transcoding for your Netflix experience. By the time you're streaming something, that's already been transcoded and inspected because that creates a better experience. So it's a very complex process to go through. It's also a very large process to go through. At its peak, our media encoding farm was running over 300,000 CPUs across 1,000 different auto-scaling groups to get some encoding work done. So after that, you end up with a pile of files. Now, what does that pile of files really mean? Any of us that have ever installed an operating system, we end up with a lot of files. Oh, let's make it a little bit more relatable. In October of this year, Netflix released Stranger Things Season 2. Stranger Things Season 2, shot in 8K, has 9 episodes. Those source files are terabytes and terabytes and terabytes and terabytes of data. It required 190,000 CPU hours just to go through the media encoding process for this one season of this one television show. To give you an idea, to map that out to kind of an instance equivalent idea, if I launched 2,965 M4 16XL instances and ran them for an hour, that would be the equivalent amount of compute that was spent to turn those source media files into things that you can enjoy on whatever device you want to watch them on. The resulting files from those original 9,570 different video files, audio files, and time text files to create that experience. This is where technically I think it becomes rather interesting. The media encoding team had 2 ways to approach this problem. We could set up a static farm of instances reserved only for media encoding, and then they'd always have whatever they needed. But if you look at this graph as a representation of their workload, that's a rather bursty workload. There are times they have more work to do, and there's times they have less work to do. So there'd be a lot of time that farm might be sitting there underutilized. If you recall from earlier, I mentioned that we auto-scale in and out tens of thousands of instances a day. Well, we use zonal reserved instances to make sure that the capacity we ever want and need is available for us. But as we auto-scale down, that means we have reserved instances, we have reservations that aren't actually being used. So we're able to create this internal spot market. So the media encoding pipeline is able to look at those reserved instances and what's currently being used and what isn't being used. And for the most part, regardless of instance type, go out and use those for those chunked encoding jobs. So that's what the graph represents, is their use of instances that were reserved but not being used by other software at the time. The colors represent different instance types. So they're able to map that job, that work, across almost any different instance type and still get the result they need. It's also it's a rather fast system. If we need to, we can start with that source material and we can push it through this pipeline and start getting it out to the CDN for you to see in about 30 minutes. So using this internal spot market idea compared to the reserved idea of a static encoding farm, they estimate they only saved about 92% of the cost of doing an internal spot market versus a static encoding farm. I thought that was pretty impressive. Security in the cloud. Netflix has a few things that we need to secure. We have content that we need to secure, we have systems that we need to secure, we have software that we need to secure, we have data that we need to secure. So we have a few different security teams with different areas of expertise. We have a platform security team, an information security team, an application security team, we have a security incident response team. The security is complex. One of the tools that we use is IAM, or IAM, and we're able to control the permissions to the different roles. Great, so we have a solution. We'll go out to our software engineers, we will point them at the documentation for this particular service and say, please make sure your security is perfect based on the ideas of least privileges. Also, as you move over time and change, make sure that you keep that updated. Again, this sounds like a successful model. Because now all of my software engineers that have other jobs to do now have to become security engineers. While this system is very flexible, currently there's a little over 2,500 different things that you can tweak for permissions on a role. So if we went with that earlier model, what would happen? I think our engineers will do their best and they'll probably grab some of the permissions that they think they need, and maybe some of them that they think they might need, and a couple of them maybe they don't need but they plan on needing. And all of a sudden now we have all of these permissions handed out that they're not using. So our security teams created 2 neat pieces of software. One is called Aardvark. Aardvark goes over the Access Advisor portion of the console, constantly combing that and pulls down that information about what roles we have and what they're actually doing and when those permissions are being used. Stores that information off and exposes it in the form of a few different REST endpoints. And then RepoKit comes along. RepoKit is able to look at that data, watch how it changes over time, see what permissions people are actually using, what permissions they're occasionally using, and maybe what permissions they've never used or they've stopped using, and then it pulls those permissions away. So now what I end up with is software engineers that can focus on the software they need to write, and a system that ensures they're still exercising those concepts of least privileges. There are a few other Netflix talks going on at reInvent. You can see there's an attractive list up there on the screen. We have, I believe, 6 tomorrow, 6 Thursday, 2 on Friday. And a lot of them do deep dives into some of the topics that I've introduced to you today, whether how we look at networking in the cloud, security in the cloud, how we use this chaos thing, perhaps, that you've heard of, how we do A/B testing, details on encoding. If you want to hear more about those 70 different applications and what it takes to actually run them, we have a talk for you for that. My name is Dave Hahn. I'm a senior SRE at Netflix. This is where you can find me on the internet. We also wanted to make sure that now that you've taken this walk through Netflix engineering shoes, that they're available to you as well. If you come by our booth, we have stickers of the Netflix engineer shoes we'd love to share with you. Doing Q&A is a little tough in a room this size. Also, we kind of have to get out of here for the next session to come in. I will be spending a lot of time at the Netflix booth, number 136 out there on the expo floor. I'll be there this afternoon and the following days. There are also much more intelligent people there to answer your intelligent questions. So please do come on by, ask some questions, pick some stuff up, figure out what it is we do at Netflix and why. Thank you again for coming.